Next, we need to review general equilibrium and KSP. Equilibrium is a huge topic on the AP exam. There is a separate acid-base review. I do like this meme. I hope the AP chemistry exam shifts in your favor. The definition of equilibrium is depicted in the first graph. You see at the top graph that the equilibrium is achieved when the rates are equal. So notice that is the forward rate of a reaction is equal to the reverse rate. So that's what those rate constants with the F, the small f and the small r refer to the forward and reverse reaction. So here's our reaction. So when those rates become equal, notice what we really think about is happening, and this is probably the most common graph we see. The reactants and products amounts become constant. Okay, so we could, if we were asked where equilibrium was achieved, again, the dotted line is already there, but if we were asked to, note equilibrium, we could tell is where those numbers become constant. We could see this from a data table where we see like concentrations or pressures become constant values. We could tell those were equilibrium values, or again, as depicted in a graph. When we're looking at the equilibrium constant, which is capital K, when we see that K is greater than 1, this is telling us that at equilibrium there are many more products than reactants, so that says products are favored. It's also depicted as saying the equilibrium system or position lies to the right, meaning the forward reaction is favored. When we see that the equilibrium constant K is less than 1, that means that the reaction is reactant favored or lies to the left, or there are many more reactants than products at equilibrium. Again, we're going to see in just a moment that K is a ratio. It's the ratio of products to reactants. So if you have lots of products divided by smaller amounts of reactants, you're going to have a large K value, but if the opposite is the case, we have a very small number divided by a larger value, then K is less than 1. So that's really where that's coming from, is it's a ratio of products to reactants. Note that K has no units, which is nice, though the very few variables have no units. K is kind of a nice change from that. And then K only changes if the temperature changes. So K is temperature dependent. When you're asked to write an equilibrium expression, there are two guidelines on the formula sheet that go with this section. There's also a KA and a and a KB example. But since we're just going to talk about general equilibrium, these are the two examples that pertain to that. So KC, C meaning concentration. Notice that we have brackets, which mean molarity. And then for KP, P meaning pressures, and we have these P's with the sub, whatever the substance is. Like if I was talking about the partial pressure due to ammonia, I would write P, and then NH3 would be kind of like a subscript. It's very important to note that, again, this generic reaction is on the AP exam, so it's reminding you it's products of reactants. Notice that the small letters, the lowercase letters, would be like coefficients, and so our coefficients, due to the law of mass action, become our exponents. On the KP expression, if you were asked to write that, you must have those P's for partial pressures. The parentheses are nice. It's great to kind of, keep up with your information, especially if you have a lot of exponents. However, I just want to say you cannot put brackets with pressures. Brackets only refer to molarities. So if you tried to mix these two together, that wouldn't work. If this was on a free response, it would be 1 point. So it has to be exactly correct. Only gases and aqueous solutions are substances that would be included in equilibrium expression, because they are the only substances that would have like concentrations, or gases could have pressures. So in other words, we're not going to include any solids or pure liquids. So watch water. Is water a pure liquid? We would not include it. If it was water vapor, a gas, we would include it. So here's just an example. Notice water is a gas, so we would include it in the expression. So first write Kc. Think about it, you need brackets, we need products over reactants. All the coefficients become exponents. And then the Kp expression, since these are all gases, these would also all exert pressure. So that's kind of what it would look like. If you did not write Kc equals or Kp equals, you actually, if this was 1 point, you wouldn't get it. This needs to look like a formula. As you see, we're going to use this as a mathematical relationship describing what's going on with an individual reaction. So how do we calculate Kc or Kp? Well, this is when we learned about setting up a rice table, or some people call it an ice table. I like rice just because you do need the reaction written there, and then the other letters ICE stand for initial change in equilibrium. So it's just a really convenient way to keep up with a lot of information in a very organized format, and it kind of helps us see what we have and what we're missing, what kind of math we'll need to do. So first we need our reaction. We'll read a problem. If we see the words, these things were mixed together, that's going to be initial. And then at equilibrium, it was, measured that this substance had a certain value. Then, again, there are keywords that we'll look for to see, do we need a rice table? Where do we put all this information? Once we have the equilibrium values, that E line filled in, then we could plug into our expression and solve for whichever K we've been asked for. So here's an example. A closed system initially containing this small amount of hydrogen and this other amount of iodine at this temperature is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is this molarity. So again, conveniently it mentions the initially and then equilibrium. So that's how I knew to set up my rice table, and then I've plugged in my values. So I plugged in the numbers as they were written, and then notice the HI is way down here at the equilibrium line. So I made my rice table, and nowhere did it say that this was 0 initially, but it also is implied because it did not mention HI. It only mentioned it at equilibrium. So that implies that it must have been 0 to start with. So that's how I came up with the table and plugged in those beginning values. And then my goal is to figure out, okay, well, and I have enough information here, since this is assumed to be 0 and now we have a value, that means that the HI increased by this value. So if I go to the next slide, you can see that meant the change was from 0 plus that amount to the same value as at equilibrium. So based on that change, I should be able to figure out the change for the other substances. Now again, think about it. If this product is increasing, the reactants must have decreased. So I've got to figure out by how much. Now watch your coefficients here, because notice there's an understood 1 in front of hydrogen, a 1 in front of I2, but there's a 2 coefficient in front of HI. So we do need to consider those when we think about the change line. So whatever this change is, and as we see that it's written there, it's twice what these other values are, which means math-wise we need to, take half of it, divide by 2, however you want to think of it. So again, it says since the reactants are in a 1 to 2 mole ratio, their changes are half what the products are. So then when I fill in those, then I actually do the math down each column. So I'm saying this beginning number plus this negative change, because again, reactants have to go down. So this is what's left. Again, I2, beginning number, plus this negative change equals what's left. Once I have this equilibrium line filled in, now I can work towards the answer. So I need to think about what was the original question, what am I asked to solve, and it was to solve for K. So once I plug these in, there's my equilibrium expression as products of reactants. Again, don't forget your coefficient would be that exponent 2, do the math, and you get 51. I've got my answer. Now sometimes we're asked, and this always reminds me of Hess's law, like if we change a reaction, we change delta H. We reverse a reaction, we change the sign of delta H. It's just when we're manipulating K for different reactions, it's more complicated because K has exponential effects when you change it. Think about it. If you reverse K, you're like flipping the equilibrium expression upside down. So if we're given this reaction in bold, and here's its K value at this temperature, and we reverse the reaction, I can't just change the sign of K. That doesn't really make sense, because think I've taken an equilibrium expression and I've taken the reciprocal of it. So I have to do the same thing to the K. So I would take the reciprocal of it, and now I have my new value, 4.72. Again, in Hess's law, we altered coefficients and we multiplied the delta H by the same amount. But with K, every coefficient becomes an exponent. So again, an exponential effect. If I decided I would take my original reaction here, and now I've taken half of all the coefficients. So I've taken half of the reaction. So whatever change I've done to the coefficients, I raise K to that power. So raising it to the half is like taking the square root. Do that in your calculator and you get 0.460. When we did Hess's law, to get an overall reaction, we just added delta H's together. If we ever need to add reactions together that have K values, we can't add them. We have to multiply them because, again, K has these great effects math-wise. Le Chatelier's principle is defined: if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. So we have to have equilibrium to start with. Something changes, and again, here's some scenarios. Number one, let's say that we add a component. Okay, so if you look at the example here, the first thing says, a change or a disturbance is we added more nitrogen. Well, if we add a reactant, the reaction will shift to use that. So that's why it's saying it will shift forward and go back to equilibrium. So again, that's mentioned here. The second part of number one says if a component is removed, the system will shift to replace what's removed. So again, if we go down here, here's an example of removing ammonia. And get rid of all this. If we remove ammonia, like if you think of it, you're taking it away, this reaction will shift to make more of it. Okay, so again, that's just if you're changing the amounts for number one. For number two, if we're told the reaction is endothermic or exothermic, or which really we would probably be told those terms, we'd probably be given a delta H value. So if we're told delta H is positive, we know it's endothermic. If we're told delta H is negative, it's exothermic. So if we are given some clue to know that it's endothermic, we need to think about, and I'll erase the arrow. If we're told this is endothermic, we should write heat on the reactant side, because you really should think about heat as number one. So if energy is a reactant, if we increase the temperature, again, it's going to shift to use that extra. Okay? If we decrease the temperature, like if we take heat away, lower, it's going to shift the opposite direction to replace the heat that's missing. Okay? Now, if you do the opposite, if we said it was exothermic, and again, we're not told in this situation which one we have, but if it was exothermic, we would write heat on the product side and think of it the same way. So if we add heat, it would shift left. If we take away heat, it would shift right. So again, you just kind of have to, again, pay attention to the clues. If you're asked about temperature changing, they must have told you somehow it was endothermic or exothermic, so you could figure out the answer. Number three refers to gases. Okay, so, and it really refers to Boyle's law. Remember, Boyle's law is the relationship between pressure and volume. So if we have a high pressure, that means the volume was decreased because it's an inverse relationship. So notice when we're looking, if it's mentioned that pressure or volume changed, look at moles of gases. So on this side, if we take this example, we have 4 moles of gases, and again, we're only looking at gases, they're only affected by pressure. And then on this side we have 2 total, so 1 plus 3 is 4, and then 2 with the ammonia. And then it depends on the shift as to where the moles are. So notice what it says. If we decrease the volume or increase the pressure, because again that's the same, doing the same thing, it's going to shift towards fewer moles of gases. Think of small volume, not much room, it shifts to fewer moles. Okay, now if we do the opposite, okay, so this time we're going to increase the volume, meaning the pressure goes down, it's going to shift towards more moles. So it would be, there's more room, more moles of gases could exist. So those are good scenarios to practice and maybe to go through the rest of those examples. This graph is nice. If we took the first graph on the slide where it showed you the reactants decreasing, the products increasing, and then they flattened out at equilibrium. This is equilibrium, where we have these equal, where these amounts are constant here. That's equilibrium. And then all of a sudden, of course, all of this would not be labeled if this was on a test question. But notice what's happened here is that there's this spike in hydrogen. So that indicates that, like we said on the last slide with Le Chatelier's principle, that hydrogen was added to the system. And notice the system has got to deal with that disturbance or that change to the system, because it was at equilibrium. Now there's a disturbance. We've added hydrogen. Notice hydrogen's a reactant. If we add a reactant, it's going to shift to use it. So we would expect the reaction to go forward, and let's see if it does. So hydrogen was added, it spiked up, but then notice it went down. Why? Because the reaction shifted forward. What else should decrease? Nitrogen decreases a little bit. And what should ammonia do since it's a product? It should go up. Now notice hydrogen goes down a lot, nitrogen barely decreases, and ammonia goes up, it looks like a little bit more. So make sure you understand why. And it has to do with the mole ratios. Notice hydrogen involves 3 moles, so it's going to have the greatest change. Nitrogen, 1 mole, and it's really based on their mole relationships, and nitrogen has a 2 coefficient. So after the disturbance occurs, the change happens, meaning the shift forward, and then what happens? Equilibrium is reestablished. Notice these equilibrium values now are different than they were originally. Okay? But if I solve for K, again, I'm saying the temperature has not changed. The K here and the K here would have to be equal because the temperature didn't change. Now, if the temperature changed, that's not true, but if the only disturbance is that we've added hydrogen, then the K would end up being the same value, just calculated with different numbers. You could be asked to calculate Q. They might not actually mention Q. They might give you a situation where you're supposed to know you need to calculate Q. Q is the same ratio as an equilibrium expression, so it's still products of reactants. If you look at this, it looks just like what was written on the formula sheet for the Kc expression. But Q is an unknown situation. We don't know if it's equilibrium. So we can't call it K unless it's for sure equilibrium concentrations. So Q, the Q comes from the word quotient. It's called the reaction quotient. And the only time, and I bolded this and underlined it because, we don't solve for Q a lot. The only time you need to solve for Q is if you're given numbers of all your reactants and products and you know K. So you'll read it because they might not tell you you're supposed to solve for Q, and you'll be wondering, I have all these numbers, what do I do? You're solving for Q because what the question will probably be is, Will more products form? Or it'll ask you about some substance in the reaction. So what you'll have to do is you'll solve for Q, compare it to the K that was given, and see which way the reaction will shift to get to equilibrium. So I like this graphic over here. If you calculate Q and Q is smaller than K, we want Q to equal K. We want to know what has to happen for Q to equal K. Is maybe the best way to say it. So if Q is too small, that means the reaction would have to go forward to get to equilibrium or to equal K. Sometimes you might solve Q and it already is equal to K, and that means, hey, these are equilibrium values. Or if you solve in the third scenario and Q is greater than K, that means you have too many products, that ratio needs to decrease because Q is too big. So it's got to go in reverse, and therefore Q could equal K. A catalyst, we talk about catalysts when we talk about kinetics because catalysts do increase the rate of both the forward and the reverse reactions. But sometimes you're asked how a catalyst can affect K, and this is kind of a trick question, and I don't want you to fall for it. The equilibrium constant is not affected by a catalyst. It's just that a catalyst speeds up a reaction and the reaction goes to equilibrium. It gets to that equilibrium position faster, okay? So, again, catalyst doesn't affect K. Now let's switch to Ksp. It's just a specific version of an equilibrium expression that's talking about salts that we consider to be insoluble. Like when we say a salt's insoluble, of course we're all assuming it's a completely solid. It's a solid in the beaker. You know, the what we don't really consider and what we can't see is that a few of the ions of the salt actually do dissolve. It's just the majority of it is the solid we see. So there are a few ions that are soluble, and that's why it's called Solubility Product Constant. So really, if you're given a Ksp for an ionic compound, which we call a salt, it's telling you it's insoluble because these K values are really tiny, and the reason they're so tiny is because they're barely forming these ions in the solution. They're mostly the solid. Okay, so these are going to be very, very tiny negative exponents. The equilibrium expression here, notice it has no denominator, or it's an understood one, because we don't include solids. So Ksp expressions are just the product, and that's why they're called solubility product, of the ions that could be in the solution. Again, brackets refer to molarity. Because we're talking about insoluble solids that have these extremely small amounts of ions dissolved in the solution, sometimes it's not called molarity. Specifically, it's referred to as solubility or molar solubility. However, the units are molarity units, moles per liter. So again, if you see the word solubility or molar solubility, look at the units. If it's moles per liter, they're talking about these bracket values. Now, occasionally I've seen them give you other units like grams per liter, and you are expected to change grams per liter to moles per liter, which is just a molar mass, using molar mass to convert grams to moles. So it's not difficult, you just kind of have to pay attention. Now, I gave several examples here because sometimes they're a little different from the problems we've done. They are similar, but sometimes this just throws students off. So I've worked a full example here. Copper 1 bromide has a measured solubility. There's that word, but again, notice it says moles per liter, so they're talking about molarity. Calculate its Ksp value. So I've given you kind of a process. If you go through this process every time you're asked a Ksp question, you should have a really good chance of getting it correct. So the first thing I'm telling you to do, if they haven't done it for you, is write your balanced dissolution reaction. So this is showing what's happening when this insoluble solid is put in water. Okay, notice the water's not there. It's not a reaction. It's just a solid forming ions which are implied in water. Okay, so you don't need to write the water. So make sure it's balanced. From that, think of what would the Ksp expression be. So because these are all one coefficients, I don't have any exponents other than those understood ones. Now this is where I'm going to use the information in the problem. So I'm thinking about what KSP is, what the dissolution reaction looks like. Then I'm looking at the value. It says copper 1 bromide's measured solubility is that number. So I wrote it under that. I wrote it here. And then I just did mole ratios. If copper 1 bromide and copper plus 1 ion have the same coefficient, 1 to 1, then they have the same molarity. And notice bromide also has the same coefficient. So that means both of these ions have the same molarity as the solid. Okay? So if the question is calculate KSP, all I need to do is plug into my KSP expression. So notice I took those two numbers. All I need are the ions concentrations, multiplied them together, which is just squaring them, and I have my answer. You could do that math without a calculator. Okay, so now I've gotten a little bit more complicated one that I wanted you to try. So again, it's the same question, it's just giving you bismuth sulfide. So we've got 5 total ions in the solution, and it has a solubility, and it gives you this number. So again, use the same process. The first thing we want to do is write the dissolution reaction. Then we want to write the KSP expression. Then we want to use this molarity or this solubility value and do mole ratios with the ions to get their concentrations. Because in this case, you can see it's probably not going to be 1 to 1. So try that, pause and try that one on your own. To check your answers, again, notice, make sure these have charges. It's Bi 3 plus and S2 minus, and those have 2 and 3 coefficients. So notice those coefficients become my exponents in my KSP expression. I have my original solubility under the solid that I was given, and then these kind of got shifted a little bit. Notice I have different answers for the ions this time. Why? Because the mole ratio is not the same. So whatever this is I'm circling nothing. There's an understood 1 there. This is a 1 to 2 relationship. For every one of these, the bismuth ion is going to be produce 2, so it's double. So I took that answer, 1 times 10 to the negative 15th times 2, so it's 2 times 10 to the negative 15th. Notice the bismuth 2 sulfide, or just bismuth sulfide, compared to the sulfide ion. The sulfide's 3 times, so I just multiplied times 3. So again, I'm doing the mole ratio, and I've written all that out. So once I have these values for my ions, now I can go back and plug into my expression I had before. You've got to make sure you remember to square and cube the numbers, and then you get some ridiculous, negative 72 power. Okay, so what do we do? Because this example is when they give you the KSP and they're asking for solubility, which is the opposite of what we've just done. So again, start the problem the same way. Start by writing the dissolution reaction of the salt, write its KSP expression, and then think about the relationship of the ions. So notice this is copper 2 iodate. We've got copper 2 plus, 2 iodate ions. Notice there's my KSP expression. This time, we don't know the solubility. All we know is this. So that means we have unknown ions, but we do know the relationship between each other. So think about, they're asking us for solubility. So plug in an X, if that is X, because we don't know it, that's what we're solving for. The copper 2 plus ion is going to be the same. It's also X because they're 1 to 1 mole ratios. But then iodate ion is going to be 2X because of the 2 coefficient. So again, I can solve this KSP expression. I just have different information this time. So notice I plugged in my KSP, I plugged in X, plugged in 2X. Don't forget to square it. So now it's 2X squared. The 2 is squared and the X, so that's 4X squared times X is how I got 4X cubed. Divide by 4, take the cube root, and you do have the answer. This is just kind of another variation on the same thing. Notice it's asking for solubility of calcium fluoride. It gives a KSP. If it stopped right there, it would be just like the problem we had before. Notice it has this other solution that's present. Okay, This is called a common ion problem. It doesn't matter if you remember that name or not, but notice that this solid has fluoride in it, and so does this. So when we say common ion, that's what we're talking about. Again, we want to go through the same process we've done. I'm trying to show you if you do this pattern, it works for many situations. Write the dissolution reaction, write the Ksp expression, figure out the relationship among the ions, and this time, when we have fluoride, we need to also remember we don't just have the fluoride from the solid, we have this other source of fluoride. So here's how I set it up. The dissolution reaction, the Ksp expression, I'm doing this just like I did before. I have X and calcium ion is X because they're 1 to 1. Fluoride is 2X. However, now I have this new source of fluoride that came from another solution. So I really have two sources of fluoride. The 2X from the calcium fluoride, which is going to be a tiny amount, plus this sodium fluoride that was in the solution. So when I plug this in, if I left 2x plus 0.025 and then squared that term, you can see this would be working towards the quadratic formula. We are not expected to use that on the AP exam. And really, realistically, this amount of fluoride is so small compared to the fluoride that was added from sodium fluoride. We are just going to make this very simplistic and plug in 0.025 because that's the huge amount that was already present. Solve for X, square it, and solve for X, and really it just simplifies it. So it's fine to think about that 2X plus that, but don't actually try to do that math because that would be very frustrating and you don't really want to spend that much time on it. You could be asked a question with Ksp, will a precipitate form? And if you're asked that, that's really a Q question. Notice if you're asked the question, will a precipitate form, you're going to know K, or Ksp in this case. So what we're looking for here is we do the same thing. We'd write a Q expression, which would look just like our Ksp expression. We'd plug in the values that were given for each ion, and then we'd be looking for Q to be greater than Ksp, because what that would mean is there are so many ions in the solution, there would be enough ions to form the solid so that we could actually see it.